All right, welcome to the last lesson of the stoichiometry unit. In this lesson, we're going to be short and sweet, and we're just going to discuss an overview of spectroscopy. And what spectroscopy is, it is a technique that we can use the electromagnetic radiation in a variety of different ways for either determining the identity of something or maybe even determining how much of something we have. The most commonly type used in spectral analysis are infrared spectroscopy and ultraviolet visible spectroscopy. We've already talked about mass spectroscopy in the beginning of the unit, and that's how we can determine the average atomic mass of something is by looking at its mass spec. And so these are some different techniques that we can also use. The first one we're going to talk about just shortly is infrared spectroscopy, just so you're aware of it. And basically it can be used for identification purposes. So in an infrared spectroscopy, the sample is passed through, and as the molecules are absorbing the radiation, they can stretch, bend, or twist, and then they will show a peak, if you will, at those spots, especially certain functional groups like OH, which when I put that on a hydrocarbon becomes an alcohol, or for instance a double bonded carbon and oxygen. And so each molecule has a unique spectrum that they have loaded in databases, and so if I were to run a sample, I could compare that spectrum with the known spectrum and identify what the molecule is most likely. The UV vis spectrum is one that's commonly used. Matter of fact, when I worked in a chemical plant, I used this every week to help me determine concentrations. And so this is going to be used for quantification, not identification. I would know what I was running. For instance, if I was wanting to find out the concentration of a colored solution, I would know what wavelength, because I can look that up, would be the wavelength of choice. I would make a calibration standards and run it, and then run my unknown against that. And so that is what Beer's law is about. And so we're going to talk about that in just a second. I want to make sure you understand that UV vis can only be used for colored solutions because they have to be able to absorb light, and a clear solution will not. And our colored solutions are almost exclusively, with the exception of lead and a few others, are going to be your transition metals. Those are the ones that produce colored ions, like copper and iron and chromium. All right, so here is Beer's law. It's simple. Big A equals little ABC. A is the absorbance at a given wavelength. A is something called a molar absorptivity. It is a constant. B is the path length of the cell containing whatever solution we put in there. Most of the path lengths are usually 1 centimeter, and C is the concentration in molarity. And so, since A and B are constant, if the absorbance is known, the concentration can be measured as well. And so the concentration of an unknown substance can be determined by comparing it to the known substances. So we create, when we do that, what's called a standard curve or a calibration curve. And when you're doing these, depending on what color your solution is, you have to choose a different wavelength. And so you want to choose the wavelength that has the highest absorbance for that particular sample. And so here's an example of, and you're going to do this in an inquiry activity, where you determine what that wavelength is, that maximum wavelength, by just testing it out, and wherever you got the maximum, that's where you're going to choose. If you're doing transmittance is exactly the opposite of absorbance. It's how much light is transmitted rather than how much light was absorbed. We tend to use absorbance and not transmittance, but both are acceptable. Here is what I was saying just a few seconds ago about a standard curve. I'm old school, so I would probably call it a calibration curve because that's what I grew up calling it when I was coming through the ranks, but it is called a standard curve. And so what was done here is the person who made this curve made the solutions up at known concentrations and then did the absorbances and graphed, and then you should be a straight line. If it's not a straight line, then you might have made a mistake. If you've got an outlier, you might have over diluted it, or had some water left in the cuvette that you didn't realize, or maybe did your calculations wrong. But it should be a straight curve if you're doing it correctly. And we can use this curve It's kind of cool and straightforward. We can use this curve to determine the concentration of an unknown solution. And so in this case, if I were to look at this curve and I would say, okay, my unknown had an absorbance of, let's say, 0.35. So the way I would use this is I would find 0.35, and I would draw a line over, and then I would draw a line down, and I would see that the concentration of my unknown is 0.5, well, molar. They only have one decimal. So that's how you use a calibration curve. And so you will have to do that in your activity. These are known to show up on AP exams as well. A quick, easy, hey, can you read a Beer's law graph? So this is the last slide, and it's just basically kind of showing you the three main types of electromagnetic radiation that we use for spectroscopy, and they are X-ray, ultraviolet, and visible. And of course, if you look at the graph, the relative energy for an X-ray is higher than visible light, and so you would expect that it would basically be able to remove more things. So visible light, of course, is exciting the valence electrons. We're going to start at the bottom and go up. It determines the identity and concentration. That's where the UV vis and Beer's law come in. So you might want to throw in Beer's law right here. The next level up is ultraviolet, and it excites or removes the valence electrons. So visible can excite them, ultraviolet can go ahead and remove them, and it will basically measure how tightly the electrons are held, and it can be used to determine the concentration of a molecule. And there's some overlap between UV vis there, and then also a little bit of PES, which is photoelectron spectroscopy. You'll get to hear a lot about that, again, in the atomic structure unit. And of course, X-rays have higher energy, so they can actually move the core electrons. So they are measuring how tightly the electrons are held by the nucleus. Of course, the more tightly the electrons are held, the more energy it takes to remove. And so you can oftentimes identify what that element was using a PES. And I expect that to show up on the AP exam. It was one of the free response questions last year. And that is where we are stopping for the day, and you will be doing an inquiry activity for Beer's law.